Okay, now you know everything that is necessary to write pretty much any program. With all the knowledge that you have so far, in theory you can write a program of any complexity. The problem, however, would be that as you write the code, you will start getting into repeating yourself. You will write the same things multiple times, and one way of abstracting would be obviously using loops. But loops only work if you execute the code in the same place. For example, returning to the problem of filling our dictionary with a for loop, we have this code. Here we set keys in D to I squared. And we fill dictionary with squares of all numbers from 0 to 19 inclusive, and then we print the state of the dictionary, and after that we start from 20 to 40 and print again. And let's say here in between we want to print all values of D. As you can see, we have repeating code. We compute the same function for different values, and this one is a very simple function, so we don't really care about it that much. But let's say we want to compute some complex function. The results are now not very human readable and are not really easy to verify. Now let's say we have originally the same equation everywhere, but we want to change the constant parameters of that function. So let's say we want to have 31 instead of 28. Now, in order to change that consistently, to make sure that our dictionary uses the same function all the time, we will have to manually go in every place where we use this equation and change the numbers there, which is less than ideal, especially if you are going to have more than 2 places. Changing this argument consistently is difficult in such scenarios, especially if you have larger blocks of text between these pieces of code. So you are not visually able to check that code looks the same. This creates a problem. If you forget to change number in one of the places, you will have 31 there still. And you really cannot validate the outcome of your code because the computation is already rather convoluted. This happens often in real-life use cases. In order to avoid this, it is advised that when you have repetitions of your code, you should extract these repeating pieces of code into functions. To extract this function, we use def keyword, and def keyword is short for define. The second part of the definition of a function is its function's name. Let's name it SumEquation. Then we need to put round brackets and colon at the end. And inside this function, ideally, we want to return something. It's not necessary, some functions might not return any value. In such case, they by default actually return none. Now we have SumEquation, and let's say we have there the same mathematical function of I. Now we can substitute our equations with a call to SumEquation. Calling a function means taking the arguments, passing it to the arguments, executing the code of the function, getting the result, and substituting the result into whatever place from which the function was called. In some cases, calling function is a target of its own, and there is no reason to expect the result, or the result is just discarded. In our case, if we run this, the result still stays the same. However, this approach that we have just used is not entirely correct. The problem is the value of I in this particular case, because it is a global variable. The global variable, and we have been dealing so far with global variables, they exist within the scope of the whole program. So let's have a look at a case when I have been local variable of some function. To do that, we will wrap our loops into 2 defines for functions, f1 and f2, and we will call them. And we will restart kernel to clean up global variables. Now, when we execute it, we get name I is not defined. The reason for that is that now variable I, that is defined here and here, first of all, those are actually 2 separate variables, and second is that they are both local within the functions in which they were declared. This is intentional for functions, because functions need to have a mechanism that will allow them to abstract code from the rest of the program, because otherwise it would be really difficult to figure out what you should name your variables in such a way that they don't collide with some other variables named somewhere else by some other person, maybe in some other library, maybe in a combination of libraries that will only exist 20 years from the moment when you wrote the code. And the direct consequence of this abstraction need is that there is no global variable I anymore, and we have not declared any value for I inside some equation. Similarly, dictionary D is a global variable still, but this is okay for this example. So, to state once again, the values of local variables do not persist outside of functions in which they were declared. We say that they have scope. In addition to that, these variables are two separate ones, even though they have the same name. If we also had global variable with the same name set, for example, to I equals 0, in cases where no local variable are defined with the same name, the global value will be accessible for reading. But the moment you will try to assign some value to it, it will become a new local variable and it will override read access to global variable. In programming, this is called shadowing, so it effectively replaces access to external variable that is outside of the scope with accesses to the value that has been defined inside the scope. As you can see, if we use global I equal to 0, this code will run and will no longer report any error, but the values are wrong. The values are now using I equals 0 for all points in our dictionary. And scoping of functions creates the need for us to pass variable values into the functions. So how do we do that so that the function can do computations properly? We have already done this with range, print, and trigonometric functions. For range, in circle brackets, we use numbers that define start and end step of the range. And those are function arguments. In case of print, we also define arguments similarly, and we pass them to print, so that print can take values of those arguments and display them. So let's input I into some equation with the following statement. So just add I inside of those brackets. And let's remove I equals 0 and restart kernel to make sure that it is removed. We still have this error. However, the error has changed. Now it says some equation takes 0 positional arguments, but 1 was given. Now, positional arguments are the one that we just provide in specific order in round brackets. There is another type of arguments, keyword arguments. We will talk about them a little bit later. For the positional arguments, we need to tell our function that it should expect an argument. Our problem is that even if you provide the value out of the variable into the function, it doesn't automatically get in. We need to get some storage name for that value. Let's name it v to make things a little bit less confusing. Because if you use the same variable name, then you still have two variables, but they will actually have the same value because you pass value into the function. So we add here v, and we replace I inside of this equation with v. And now this function finally works as expected. So it gets the same value that we were getting originally before the refactored code, but now instead of being passed via global variable, it is passed via an argument to a function, and it is assigned to a local variable v, and it is used in the equation. This is how we pass a single positional argument. However, in some cases we might need to pass more than one variable or more than one argument. And already with range function and print function, we actually do that. So let's expand our equation so that we have more than one passed argument. Let's pass a constant that will be in our case 2 here and 3 in the next one. It is just as simple as adding a comma and another argument on the list. And in the function itself, you also need to add a comma in the list of arguments so that the function can take and just assign a new name for the second argument. For example, let's name it arg2. And let's substitute our powers with arg2. As you can see, the value 3 has changed the second half of our array because we now have different power applied to all these equations. Now these arguments are called positional arguments because their values are assigned by position, For example, in the first call to some equation, the first value from first argument v will be assigned from variable I, and then the second argument for the argument arg2 will be assigned from constant 2. However, this is not the only way to assign arguments. You can also use variable argument list, and syntax for that in Python is as follows. Put an asterisk and write some variable name. In this case, it will be varg. And this varg is going to become a list containing all positional arguments that we have passed to the function, regardless of the amount of arguments that have been passed. In this case, we have values of I and 2, and this varg will become a list that contains values of I and 2. To access those, we will have to use list notation, so we put the variable name varg and then index of the element that we want to access in brackets. Here v is our argument 0 and arg is our argument 1, so this notation works exactly the same as what we had before. But now we no longer have two variables v and arg, but instead we have a list varg that contains values for both of them. So these are positional arguments and how you can use them. Contrary to positional arguments, there are also what is called keyword arguments. The keyword arguments are defined in the functions as follows. With this notation, we are actively declaring that first value will be assigned to variable v inside the function, and right now it will do exactly the same. But the great thing about that is that it doesn't really matter in which order you pass keyword arguments, so you can change the order. The only limitation is that you have to pass all values that you want to use as positional arguments first, and all keyword arguments after that to avoid ambiguity. As you can see, even though we have passed the argument 2 as first value and I as second value, it will still return the same result. Similarly to the list of variable arguments that we used for positional arguments, where we were able to package any number of positional arguments into a single list, we can have a dictionary that will contain any possible keyword arguments. Let's name it KW, and let's use it to extract values for v and arg2 from the dictionary. And pay attention to having these two asterisks in front of that KW variable name. So we assign arg2 to KW dictionary accessed by key arg2, and v will assign from KW accessed by key v. We can of course directly substitute this into equations, but this way is cleaner. And as you can see, the results are still the same. However, this will stop working in situations where you want to pass one of these two variables as a positional arguments. You cannot mix positional and keyword arguments in that way. However, you can mix variable argument list and dictionary of keyword arguments together. But that will require a lot of manual processing. So what is good about the approach with keyword argument dictionary? Well, the primary thing is that if you add some other keyword argument, for example p = 50, to a normal function, it will fail because it will not be able to assign the value. But if you do that to a function that has a keyword argument dictionary, then assignment of an extra keyword argument will only result in that argument being added to the dictionary. The Python stops checking the arguments once you have this keyword dictionary. However, whether this argument is present or not, we can try to get its value in the function. In order to do that safely, we will need to add a check for its presence, of course, in the dictionary, because if it's not present, that will raise an error. Let's add a check for presence for p. And to do that, we're using membership operator in that will test whether this key is present in this dictionary, and if it is, then it will return true, otherwise it will return false, and this block will not be executed. If it is, then we want to print out the value of that passed argument and return that passed argument directly into the result of this function, effectively overriding this whole equation. And this one requires actually a fix. Okay, now as you can see, we have value of p printed multiple times, and it is correctly set to a lot of values here. So basically first 20 values are set to 50 here, and in the extended version they are still 50. This kind of checks and approach is useful to make flexible functions that can serve multiple purposes at the same time, although it might not be extremely good approach in all cases, but sometimes you just need to add one small feature to otherwise pretty robust function, so this might be an option. It is also a very useful thing to have flexible constructors for objects when we are going to use object-oriented programming, but we are going to discuss that use case later. There is an alternative way to define functions that's called definition of a lambda function or definition of an anonymous function. We will talk about this more when we are going to talk about functional programming in Python. But the default way to declare functions is using def keyword and by providing name of the function and the list of arguments that the function will take. Then after a colon, you will have an indented block that will define the code of the function that will be executed every time some piece of other code calls for that function. And within that function, you can do some calculations or analysis, and you can return values. You don't have to return value at the very end of your function. You can actually also return your value anywhere within the code of the function, and that will immediately terminate the execution of the rest of your function, like in the case above. There, when we have p provided, the value returned by function is set to the value of p, and the rest of calculations never occur.